Welcome to this explainer, where we're going to take what usually feels like a really dry math concept and completely flip it into a genuine investigative superpower. We so often think of calculus and algebra as just numbers on a chalkboard, but today, we're actually going to look at them as a specialized toolkit for uncovering hidden truths about exactly how our world changes. Let's just dive right in. So, ask yourself this. What do a homicide investigation, a viral pandemic, and a buried ancient artifact all have in common? Now, on the surface, absolutely nothing, right? But underneath, their hidden mechanics are actually governed by the exact same mathematical principle. And the answer is that all of these mysteries are solved using a very specific type of equation that tracks the exact rate of change, the first-order differential equation. It's basically our mathematical magnifying glass. See, a first-order differential equation models things that change at a rate depending on the thing itself. So the hotter a cup of coffee is, well, the faster it cools. The more rabbits you have, the more baby rabbits they produce. It's all about pinning down that exact rate of change. Now, how we actually solve these is incredibly satisfying. We feed our human urge to organize by literally pulling the variables apart. We aggressively push all the y and dy terms over to the left side of the equals sign and shove all the x, t, and dx terms to the right. We are literally dividing the problem into two totally isolated, manageable halves. And it really comes down to a precise three-step interrogation to algebraically pull a timeline right out of the math. Step 1, you separate the variables, just like we talked about. Step 2, integrate both sides separately. And step 3, simplify it down to find your equation. Oh, and you can never, ever forget to add the constant of integration, plus c. That constant represents our specific starting point. And just like that, we transform a really messy rate of change into a totally precise predictive timeline. Let's crack open case file 1. How long has this body been here? Imagine you're walking into a crime scene. To verify alibis, we desperately need to know the exact time of death. To solve this, we rely on Newton's law of cooling. This basically just means that the rate of change of a cooling body is directly proportional to the difference between the body's temperature and the ambient temperature of the room. I mean, think about it. A steaming hot body in a freezing cold room is going to cool down way faster than a warm body in a slightly cooler room. We model this exact temperature drop using a decaying exponential formula. So the investigators log some incredibly precise data for us. Discovery time is exactly noon, and the body temperature is 82 degrees. 2 hours later, it's dropped to 72 degrees. And the room's thermostat, it's locked steady at 65. By using our separated variables, we use this specific data to isolate the totally unique cooling constant, our K-value, for this exact crime scene. Once that formula is built, we just run the clock in reverse up the cooling curve. The math calculates that it took exactly 1.54 hours for the body to cool from a normal 98.6 degrees down to the 82 degrees we found at noon. So, time of death, exactly 10:28 a.m. Boom! The math literally leaves zero room for doubt. Moving on to case file 2. When does a viral outbreak run out of hosts? We're switching gears here from forensics to biology to track a terrifying microscopic suspect. 1,200. That massive number was the projected infected population in early COVID-19 data out of Nepal after just 21 days. Starting with only 150 cases and doubling every 7 days, our differential equation accurately and kind of scarily models this massive jump. And here is that terrifyingly steep, exponential curve of unrestricted virus spread. This happens when the mathematical growth rate is strictly proportional to the current population. The more people who get sick, well, the more people they infect, which creates this continuous, accelerating upward spike. But we know that in the real world, this line absolutely cannot go up forever, right? Because eventually, viruses run out of resources, which in this case means they run out of uninfected people to spread to. And that is exactly where the brilliant Verhulst equation comes in. It introduces a maximum population limit, which we call K, into our differential equation to account for resource competition. It brilliantly modifies the math so that as the infected population gets closer and closer to that K limit, the rate of change automatically slows down. So, compare that endless upward trajectory of the free virus to the smooth flattening of the logistic curve. Through the separation of variables, we can integrate this complex limit right into our model. And the result? You get this beautiful S-shaped curve. It starts off exploding exponentially, but then elegantly flattens out into a horizontal line as those real-world environmental limits are finally hid. It's a perfect mathematical mirror of biological reality. Okay, case file 3.
How old is this ancient artifact? Believe it or not, archaeologists don't just guess, they use the exact same mathematical toolkit that we just used at the crime scene.
And it all revolves around this concept of a half-life, which is the predictable time it takes for exactly half of a radioactive substance to decay. See, unstable isotopes like carbon-14 decay at a completely natural, constant rate, and that provides archaeologists with a highly predictable geological clock. Just like the cooling body, the rate of decay is strictly proportional to the amount of material that's currently present.
By separating the variables, we calculate exactly how much material decays over, say, 10 millennia. If we start with a 100-gram sample of carbon-14, which happens to have a half-life of 5,730 years, our differential equation can project exactly how much will be left after 10,000 years. The math gives us exactly 29.7 grams remaining. By comparing carbon levels in an ancient bone to this exact curve, this equation literally becomes our ultimate time machine.
But hold on, before we close the book on all this, we have to talk about the detective's blind spot. What crucial detail gets lost in all this algebra? Well, a classic MIT calculus lecture actually gives us a really critical warning here. In mathematics, moving too fast can actually cause you to completely erase a valid reality.
See, by aggressively shifting our y variables across the equal sign through division, we run a huge mathematical risk. We risk accidentally dividing by 0. In our total rush to separate the variables and integrate, we divide by the function of y. But what if y is exactly 0? When we do that, we unwittingly erase what's called the trivial solution, the parallel universe where nothing changes at all. Think about it. If the population of a virus starts at 0, the rate of change is 0, and the population stays at 0 forever. That is a perfectly valid mathematical solution, and it's an incredibly important physical reality. But because we divided by y, our grand algebra just completely misses it. We blind ourselves to the absolute simplest truth. And it leaves us with a pretty provocative thought to end on. If the simple act of dividing an equation can completely erase a valid reality from our models, what other quiet truths are slipping through the cracks of our equations? As we use math to conquer the mysteries of the universe, we really have to wonder what hidden realities we might literally be dividing out of existence. Thanks for joining me on this explainer, and keep questioning the math.